All right, welcome back to Calculus 1. In this video, we're going to learn about a way to find derivatives for inverse functions. So let me pull up our slide here. All right, and we should be good to go. Okay, so we're going to split this kind of video, this lecture, into three parts. We're going to first do a quick review of what inverse functions are. So you might recall through your pre-calc course learning about exponentials, and then their inverse is logarithms. So we're going to take a quick review of that. And then the second and third parts, derivatives of logarithms, and then derivatives of inverse trig functions. Parts 1 and 2 will be in this video. There'll be a separate video for part 3, derivatives of inverse trig functions. Okay, so let's get to the review. So a quick brief review of inverse functions. You might recall kind of in the maybe halfway point of your pre-calc course, you came up with this way to define an inverse function. All right, keep in mind the notation. F of x denotes the function. That notation, what looks to be f to the -1, that's what we use to denote the inverse function, which is basically the opposite. So just be careful. That notation, the inverse function notation, that -1 is not an exponent. It looks like one, but it's not. It is bad notation. If you did interpret it as a -1 exponent, you get this result 1 over f of x, which it is not. So that inverse function notation, f to the -1, denotes the inverse function not reciprocating. So just be cautious of that. All right, with a function and its inverse, they should cancel out. And we have these two inverse properties, or what are called the cancellation properties. So that's when you plug one function into its inverse or vice versa. They should cancel out to give you what you started with, which is x. So keep that in mind. You've seen that in a few places through algebra. You first introduced squaring, and then shortly after that, you talked about the opposite of squaring, taking a square root. And similarly for nth powers and then nth roots. So you might be familiar with this conversion formula, converting back and forth between squaring on one side and then square roots on the other. So think of this as a way to translate from one form to another. In your pre-calc course, you might have called this converting from logarithmic form to exponential form. So what's the point of reviewing inverse functions? Well, notice on the right-hand side of all those conversions from square roots, nth roots, and logs, those are now defined implicitly. They define functions, but now they're not solved for y. So the thought is, what we're going to get to, if we're talking about derivatives of inverse functions, we might use this converted form and combine it with implicit differentiation. Notice on the right-hand side there, y squared, you can use the power rule, e to the y, the exponential rule. The right-hand sides there in implicit form are going to be much easier to work with. All right, so that's basically for part 1. You might want to go back and review some topics from your pre-calc course if needed on inverse functions. Let's get to part 2, how we're going to find derivatives of logarithms. And remember, logarithms are inverses of exponential functions. All right, so we're going to start with a simple derivative, the derivative of e to the x, which is itself. The question we're now going to ask is, what is the derivative of natural log of x? That we currently don't know. We could try using the limit definition of the derivative. That's going to get kind of rather messy. So instead, we're going to try to go through finding the derivative of natural log of x using implicit differentiation. All right, so we're going to start with the, I'll say equation, y equals natural log of x. All right, and what we're going to do is convert that into basically implicit form. Now with y as natural log of x, we're interested in finding what is y prime. All right, so if we go back to y equals natural log of x, let's convert that. We get e to the y equals x. And now we know what derivatives of exponentials are. So we're going to combine this with implicit differentiation. We're going to take that statement e to the y equals x. We're going to start by differentiating both sides with respect to x. Notice both derivatives on the left and right side are rather simple. E to the y times y prime, and then the derivative of x, 1. And from here, we can basically solve for y prime. We get that it comes out to 1 over e to the y. But since we're starting with a function of x, natural log of x, we'd want to know what its derivative is in terms of x as well. So if we convert this answer with y back in terms of x, we can go back to our original equation that we were starting with. E to the y equals x, what we converted to implicit form. And if we just plug in there e to the y as x, we get our derivative as 1 over x. And that is the derivative of natural log of x. So we kind of have our first new differentiation rule from which everything else is going to build, that the derivative with respect to x of natural log of x is 1 over x. All right, so let's go ahead and put that to use with some pretty basic examples. We'll do 2 here. Notice for each of these, we have natural log, but functions inside. And when you have functions inside functions, we use the chain rule to find those derivatives. All right, so you might want to pause the video here, give these a attempt, and we'll check back in a few minutes. All right, welcome back. So let's go through part A. Remember, we're going to use the chain rule here. We want to take our divide and conquer approach. So identify your outer and inner functions. Outer function is natural log of x, and the inner function 1 plus x squared. Both those derivatives are rather simple. 1 over x, which is new, and the derivative of 1 plus x squared, 2x. All the work is done. We just now combine the pieces back with the chain rule. The chain rule says our derivative is f prime of g of x times g prime. And if you plug 1 plus x squared into 1 over x, you get that fraction, and then the 2x is the derivative of the inside, g prime. And now we can rewrite as a single fraction to clean it up a little bit, and write that as 2x divided by 1 plus x squared. Okay, let's look at part B. Part B is also going to require the chain rule, since we have functions inside functions. Start off by identifying your outer and inner functions. The outer function here is still natural log of x. The inner function is now sine of x plus cosine of x. The derivatives are rather simple. Keep in mind your basic trig derivatives. And if we combine the pieces back together with the chain rule, f prime of g of x times g prime, we get this expression. That again can be expressed as a single fraction. We clean it up a little bit and we get that. All right, now with these 2 examples out of the way, both which came from applying the chain rule, there is a kind of a nice pattern you might observe in the end results for y prime, the derivatives here. And notice both of them, for the respective inner functions, g of x, the end results have the form g prime of x over g of x. And that's going to lead us to a very nice shortcut, kind of our last special case of the chain rule, something that we'll call the general logarithm rule. All right, so before we get to the new version, let's review some of the special cases of the chain rule. We had what we first called the general power rule, where the outer function is x to the n. But now we have maybe the function, a function raised to the nth power there. So we have this familiar rule which we used before. Again, a special case of the chain rule. We had a related version, the general exponential rule, where you have e raised to a function. Here the outer function is e to the x. And we get this nice simple rule. The new version, what we're going to call the general log rule, is the special case where we have a function inside a logarithm. And the outer function here is just natural log of x. If we combine that with the chain rule, we get this nice simple form, g prime over g of x, for what we're going to call the general log rule, for when we differentiate functions inside logarithms. All right, let's take a look at a quick example putting that to use. Let's go through the example finding the derivative of ln, natural log, of x plus tangent x. So all we really need to look at is the derivative of the inside, x plus tangent of x, and apply the general log rule. X plus tangent of x has a simple derivative. X differentiates to 1, and tangent of x differentiates to secant squared. Notice in the denominator is the original function that fits the form for the general log rule, the derivative of the inside over the inside function, g prime of x over g of x. Now, the general log rule, we're going to use that kind of in a shortcut, which we'll be getting to right after this. And the general log rule is going to make this, this shortcut go as quick as possible. All right, so the last topic that we'll get to in this video is called logarithmic differentiation. And this is a kind of a shortcut technique for differentiating complicated functions. All right, so let's take a look at some examples where we might have complicated functions. So here's 3 of them. Notice going down, we have a complicated product, complicated quotient, and then a complicated exponential. And these are going to be good examples for us to apply the technique called logarithmic differentiation. Now that first one up there, the complicated product, we can differentiate that using combination of the product rule and the chain rule. But for some problems that could take a while, we might want an alternative approach, something that's a little quicker and more efficient, which for these examples, the general the logarithmic differentiation will be that shortcut. All right, in order to apply logarithmic differentiation, kind of the main idea why it works is we first simplify the function using properties of logarithms. And that's going to allow you to split products, quotients apart into individual logarithms. So before we get into kind of how this works in calculus, here are our 3 properties of logs. And we're going to kind of apply all 3 of them to certain problems. All right, so we're going to take a look at a quick review example first. Notice here the 3 properties of logs come from basic exponent rules. So keep in mind, logarithms are exponents. All right, so here is our quick review example. This is something that you would have covered back in your pre-calc course. The question would have been stated then, use the properties of logs to write natural log of x squared times x minus 1 divided by 2x plus 3 as a sum or difference of logarithms. So essentially what we're going to do in these examples is split a single logarithm into multiple logarithms. All right, so we start with the original logarithm. And since we have a fraction in there, we notice we can apply property 2 of logarithms. So the second property relates to division to subtraction. So we basically get it as a natural log of the numerator minus natural log of the denominator. All right, notice in that first part, we still have a product. So we can split that apart using property 1. And then in that first term, natural log of x squared, we have an exponent, which we can bring down using property 3. So we can bring that exponent 2 down as a factor of 2. And that's basically what we're going to do in the process of logarithmic differentiation. But this is not calculus. This is just simplifying the function first. And then after that, once we've split it apart, we'll take derivatives of both sides. All right, so before we get to some examples, let's just do a quick kind of set of steps for what will be involved for using logarithmic differentiation. So most of these functions, if you think back to the 3 examples we had up on the screen. So we had the complicated product, complicated quotient, and complicated exponential. None of those have logarithms in them. So our first step in applying logarithmic differentiation is to take the natural log of both sides. Now, once you've done that, you can then use the properties of logs in step 2 to simplify the complicated side, split it apart using the multiplication addition property and division subtraction property, property 1 and 2 of logs. Once you've fully simplified that as much as you can, we're going to differentiate both sides with respect to x, keeping in mind, maybe you want to think of when you differentiate y using implicit differentiation. And once we differentiate both sides, it's just a matter of solving for y prime. And what makes this go really quick in step 3 is using the general log rule, which is why we introduced that a few moments before. Okay, let's take a look at 3 examples on using logarithmic differentiation. So there's 3 of them there. Pause the video, give them a try, and we'll check back in a few minutes. All right, welcome back. Let's go through part A. So for this complicated product, first step, take the natural log of each side. Since we have a multiplication inside and exponents, we can apply property 1 of logs as well as property 3. We can bring the exponents 3 and 2 down as factors. All right, that's about as simple as we can make it using the properties of logs. Next step, you can differentiate both sides with respect to x. We're going to use the general log rule twice for the right-hand side and its derivatives. We're going to use implicit differentiation on the left side. So keep in mind, the derivative of ln of y would be 1 over y, but times y prime, since we're differentiating something with y in it. So if you apply the general log rule, we get this expression for the derivatives on both sides, and we can easily solve that for y prime by multiplying both sides by y. And to get a nice kind of clean answer, we generally want to have our derivative only in terms of x, since the function is only in terms of x. And we can just plug in the end there, that factor of y, as what y is from the beginning of the problem. And we get our y prime there, our derivative, maybe a little quicker than if we would apply a combination of product and chain rule. All right, let's move on to part B. This one is a complicated quotient. So when we take the natural log of each side, our kind of first step in simplifying that right-hand side is using property 2, the division property. All right, that basically splits this into natural log of the numerator minus natural log of the denominator. But be careful, notice the denominator has 2 factors in it. So you're going to be using property 1 for the terms in the denominator. And just be careful, from applying property 2, the minus is going to affect the 2 logs you get from applying property 1. Also notice the square root in the denominator. You can think of that as a 1/2 power. So you can apply property 3 to bring that 1/2 power down to that last logarithm, which is where 1/2 times natural log of x squared plus 1 comes from. So for this simplification, we applied all 3 properties of logs property 1, property 2, as well as property 3. Now we can differentiate both sides with respect to x. We're going to use the general log rule 3 times on the right side, combined with once on the left side with implicit differentiation. Left side is going to differentiate to y prime over y, and then we apply the general log rule 3 times, derivative of the inside over the inside function. And then like in the last example, multiply both sides by y and convert back your y in terms of x. All right, and for our final example, part C, this was our complicated exponential function, 1 plus x raised to the sine of x power. Now this is an interesting example. None of our previous rules, basic product rule, quotient rule, or chain rule would work to find the derivative of this function. So with logarithmic differentiation, we now get a way to find this derivative. All right, so when we start by taking the natural log of each side, since we don't have any products or quotients, we can't apply property 1 or 2 of logarithms, but what we can apply is property 3, bringing that exponent, sine of x, down as a factor. And since we now have that coming down as a factor, sine of x multiplies natural log of 1 plus x. When you go to find that derivative of the right-hand side, you're going to have to use the product rule. All right, we're going to differentiate both sides with respect to x. The right side now requires the product rule. Okay, and at this point, once you differentiate both sides, again, the left side is always going to differentiate to y prime over y, multiply by y, and then convert back your y in terms of x. All right, and that is it for this video. Definitely go back, review the examples, pause, and stay tuned for more online lectures as we continue our course.